Bone saw is ready. Okay, so here we go. This is a convex mirror example. So here's our convex mirror. Here's our object out here. Remember, our focal point is on the inside of the mirror, and the center of curvature is on the inside. Even though the mirror is out here and everything in here is dark, that's still where the focal point and center of curvature are. So if we want to determine the locations of the image using a ray diagram, I'm not even going to worry about the numbers right now. I just know the following. First, ray strikes the mirror, and I try to draw this as flat as possible. If I'm doing this in a AP setting, I make sure I have a straight edge or something so that I can draw this nice and straight to strike the mirror. Technically, this ray begins to bounce off like this, but if we draw it just right, what we'll notice is that this ray is actually being backtracked through the focal point, such that, that ray could run backwards like this, okay? So that's the first ray we made. Or this right here, this is like a virtual ray. It's not actually there, this is all dark, but we can backtrack this ray through that. The second line we make, we go from the top of our object and we run it all the way to the center of curvature, okay? That's how we take care of this one. So let's just take a large line, run it through the center of curvature here, boink. And where these lines intersect, that will be our image. So right there, that's the tip of our arrow. And the reason why we can send that all the way through the center of curvature is technically when this line strikes right here, it reflects back in the exact same path. So we just backtrack it through the center of curvature, and this is our image. So that's just how we can set up the ray diagram. If we want to determine the location and magnification analytically with numbers, we should know this. So this is a external, so the right side, rear view car. It's convex. That's why objects always appear closer, objects are closer than they appear, that little saying. We know the radius of curvature here, C, is 16 meters. The object is located 10 meters away, so this is DO. Because C is 16 meters, we actually know that the focal length is half of that, so the focal length has to be 8 meters, and DO is still 10. So if we want to find the location, if we set up our mirror lens equation, 1 over F equals 1 over DI plus 1 over DO, then we'll get 1 over 8 equals 1 over DI, which is what we're actually looking for, plus 1 over 10. And we got to be careful when we run this math here. We need to make sure that we're not just like subtracting 10, like we're not doing something dumb like this, like that. That's so garbage. Don't do that. We need to make sure that when we subtract 1 over 10 from each side, this is like 1 over 8, and you do that minus 1 over 10, and you do these fractions independently, and then this equals 1 over DI. We reciprocate at the end. So running this, 1 divided by 8 is 18.125, and then we subtract that, we subtract 1/10 from it, so 0.1. And when we do that, we just get 0.025 equals 1 over DI. And then now that we reciprocate this, we take each side, do 1 over that value, right? So we're going to get 1 over 0.025 equals DI. And when we do this, we're going to find here, what is that? 1 divided by 0.025. We're going to get 40. So that should be 40 meters there. Okay. Now, if you take this, and we wanted to find the magnification from it, the magnification equals negative DI over DO. And if we ran this, we'd get here that this would be like negative 40 over 10, which would be 4. And if you've just been following along with that, something's wrong, and it messed a whole bunch of stuff up. Pause this, see if you can figure it out. Okay, did you get that? Well, here it is. Because our convex mirror has a dark side and our focal length is on the dark side, the focal length for a convex mirror is a negative value. So our focal length here is actually -8 meters. It's negative. So that means when we go back into this equation here, we're going to have a lot of things to modify. Because this is a -1/8, to solve this, we're going to have to, kind of mix things up a little bit. When we take -1/8 minus 1/10, we're not going to get 0.025. We're going to get something different. If we actually take a look at this, we can run some common denominators here, or we can just do it however we do. But -1/8 minus 0.1, that's going to give us, let's see, should give us something like -9/40 if we do that with common denominators, and that would be like 0.225 or -0.225. So if we come down here, 1/-0.225, because that's our new value, and we take the reciprocal of it, that doesn't give us 40 meters. That gives us 1/0.2222. That gives us -4.4 repeating meters. So this is why the objects are closer than they appear. That object has this value of -4 in this case. It has a different look because the fact that our focal length here was negative. This also means when we take this and we put it into our magnification equation, we have a negative in the equation itself, and we have a negative in the number. So we're going to get the negative of a negative, a positive, 4.4/10, which doesn't give me 4. It gives me a fraction, which is going to be 0.44. So our magnification here is 0.44. We see it's a number less than 1, so it's smaller. So the object looks small, but it's actually closer. It looks smaller in the mirror than the object actually is. And because this is a positive value here, we know we didn't flip the image. And because we didn't invert or flip the image, we know it has to be virtual, which is exactly what we saw up here in the ray diagram. If we went down here and got that -40 or the -4 from before, we'd be like, wait a second, how could it be negative? It has to be positive because I didn't invert the image. What did I do wrong? Well, the thing most people do wrong is they forget this. So let's make that mistake this time and never make it again. Okay? So until next time, this is finished. Adios and take it easy.